Good afternoon and good evening, everybody. My name is Wei-Lei Wang. I'm from Xiamen University, which is located in a beautiful city, Xiamen, in the southeast of China. So I welcome everybody to come to visit us in the near future. So today my topic is using multiple hydrographic tracer to constrain the biological carbon pump, which is a recent study just published in last December in Nature. So before I get started, I would like to acknowledge my co-authors they are Francois Primo, Yi Liu, and Wei Fu from UC Irvine, Fred from Le Mans, and Robert Lester from the University of New Hampshire, and Jiming Tang from Xiamen University here. No matter what your background is, I bet everybody is familiar with this figure. They are the atmospheric CO2 concentration versus time. As you can see from this figure, the CO2 concentration reaches the highest level in the over 800,000 years. So CO2 is a greenhouse gas. The increased concentration in the atmosphere due to the climate change. The top two panels compare the temperature in the end of the century to the beginning of the century. So even with the strong climate mitigation, as we can see in some regions, the increase of temperature over 1.5 degrees C. At the business as usual or high emission scenario, the increase of temperature over 10 degrees C. Another impact is on the precipitation, as shown in the bottom two panel here. The influence on precipitation is not even. Some places get wetter and some places get drier. The third impact is on the ice cover in the North Pole and the South Pole. The top two panels compare the ice cover in the 1984 and the 2012. Over the 30 years period, the ice cover shrink almost 50%. Also, CO2 is after dissolution into the seawater, it becomes to carbonic acid. So the increased concentration of CO2 in the atmosphere lead to ocean acidification that have a strong impact on the coral ecosystem. This figure summarizes the sources and sinks of CO2 in the Earth. As we all know, the major source is the fossil fuel combustion and land use changes. Where it goes to some of them lives in the atmosphere, and around 30% goes to the land, and 26% goes to the ocean. As an oceanographer, I'm more interested in the ocean sink. The biological carbon pump is a key component of the ocean sink. So in the ocean, in the euphotic zone, phytoplankton synthesize CO2 into organic matter. So this organic matter, some of them are consumed by zooplankton to make fecal pellets. The fecal pellets and the dead body of phytoplankton and zooplankton sink in the water column that transport carbon from the surface ocean into the deep ocean, where it stays for a long time. On the right, I list the three facts about the BCP. The first is the present-day CO2 concentration will be twofold higher without BCP. The second, BCP accounts for 90% of the vertical DIC gradient. However, the current estimate of the BCP still have a large uncertainty from 3 to 12 petagram carbon per year. So this uncertainty is not reflected in the integration number, but also on the spatial distribution. So these four panels are from 4 previous studies. As you can see from the 4 panels, the spatial distribution are really different. So here you may ask why, after so many years of study, our estimate on BCP still have so large uncertainty. The answer is quite straightforward and simple. That is because the BCP is really complex. So as summarized by Boyd et al. In this figure, from right to left, from left to right, we can see there are multiple pathways. First one is a gravitational pump, and the middle two are associated with the physical transport. They are anti-subduction pump and mixed layer pump. The last two are associated with zooplankton. They are migration pump and lipid pump. So these pathways works on different spatial and temporal scales and influenced by chemical, physical, and biological processes. However, these processes are not well represented in our Earth system models as summarized by Hansen et al. In this table. So in this table, the first column shows the processes that can influence the BCP, and the second one represents how many models include these processes, how many models do not include these processes. The third one shows if we omit these processes, what kind of bias it will lead to our estimation. And the fourth column shows the impact on the future prediction. So I don't think I have time to go through each of these processes, but let's take the first one as an example. The first process is the fragmentation. As we can see, among the 19 models, only one model includes these processes. The other 18 models do not include these processes. Without this process, it leads to a positive bias on our current estimate, but the future prediction is still uncertain. So here we ask if the inverse model can better estimate the BCP. The basic theory behind this is no matter which pathways if the organic matter follows to the deep ocean, it eventually eliminates back into inorganic carbon. And in this process, it will consume oxygen and influence the alkalinity distribution. So if we can reproduce the distribution of these tracers, we can back calculate how much carbon are exported from the euphotic zone. So another point is over the past few decades accumulation, we have abundant observation on these tracers. For example, this 4 panel shows the sampling density of DIP, that is dissolved inorganic phosphorus, DIC, dissolved inorganic carbon, and alkalinity, dissolved oxygen. So this 2 panels shows the sampling density for DOC. I separate them into different hemispheres according to time. And on this side, we show the sampling density of DOC. Compared to the other 4, the sampling density, the coverage is not as good as them, but it still covers all major basins. So with this in mind, we built the most sophisticated inverse model so far that couples the cycling of phosphorus, carbon, and oxygen. I will not go into detail of each of the processes represented by the arrow here, but I want to point out that in the carbon model, we included the labile DOC and the refractory DOC here. So different from the forward model, we do not need to time integrate the model to get a steady state solution, but instead we solve the model equations analytically, either using Newton method if the system is nonlinear, or use the direct matrix inversion if the system is linear. After we solve the analytical solution, we can write down the error functions as shown by the 5 equations here. Further, if we assume this error for normal distribution, and then we can combine them into a likelihood function as the bottom equation shows. So our objective is to maximize the likelihood function or minimize the negative of the likelihood function by optimizing a set of model parameters. So here I'm going to show some results. This 4 panel shows the tracer plot for DIP, DIC, alkalinity, and dissolved oxygen. On the top, I write not surprising but still impressive. The reason why I say not surprising is because we use this tracer to train our model. We expect to get a higher R-square values. But to get such high R-square values, the results are still very impressive. So here, the panel A shows the tracer plot for DOC. Also, as compared to the other 4 tracers, the R-square value is lower, but it still explains 80% of the data variance. To make a more comparison, we compare DOC concentration with at 3 ocean stations: Ocean Station Papa, Bass, and Caracal. So in these 3 panels, the box plots represent the field measurement, and the green triangle represents our model prediction. As you can see, at these 3 stations, our model reproduce the field measurement very well. So we have confidence to calculate the BCP. Or otherwise, in other words, we calculate how much carbon exported from the euphotic zone. So here we separate our flux into vertical flux and mixing flux. The vertical flux include any flux that have apparent downward vertical movement. For example, the gravitational pump and the Zooplonk migration pump. The spectral pattern is not surprising, and we have low vertical flux at all subtropical gyres and high flux in the Southern Ocean convergence zone and the equatorial upwelling regions, and also moderate latitude in the North Pacific and North Atlantic. To validate our model results, we compare the vertical flux with to the sediment trap measurement at 4 stations: Ocean State Papa, Bass, and Aloha, and Caracal. So once again, the box plots represent the field measurement, and the green dots represent our model prediction. The thing I want to point out is that we do not use the sediment trap measurement to constrain our model. Therefore, the sediment trap measurement represents external validation. So as you can see from the 4 panels, our model have good correlation with the field measurement at all stations. So here I'm going to show some results about the mixing flux. And this figure shows the production and the export of the label DOC. So from the left panel, we see in the North Atlantic Ocean, the production is low, but as you can see in the right panel, the export is high here. The reason here is because this region are deep water formation regions. Even though the production is low, the deep water formation is going to bring the organic matter to the deep ocean that leads to the export. Another region of interest is the equatorial upwelling regions. So as you can see, the production rate here is really high, but export flux is really low. That's because the upwelling retain the DOC in the surface water, so they have no chance to export it to the deep ocean. The bottom 2 panels show the production and export of semi-labile DOC. Different from the labile one, the semi-labile DOC has long residence time in the ocean. So as you can see in the equatorial upwelling regions, the production and export are both high. To combine them together, we got a total organic carbon flux. The left panel shows the spatial distribution. And here we see the export flux at the euphotic zone, model euphotic zone, that is the top 2 layers of the model, which is 73 meters. The flux is 15 petagram per year. But if we normalize them to the 100-meter depth, it comes to about 11 petagram per year. So the flux is really sensitive to the depth horizon where we choose to estimate the carbon flux. Then again to validate our model flux, and we compare the total flux at the North Atlantic Ocean and the Pacific Ocean. We compare our results to the tracer estimated ANCP, that is annual community net production. So in this 2 panel, the black one shows the model results and the red bar shows the field measurements. Except a few points, and our model matches the field observation very well. So here, from another perspective, from the time, from the sequestration time perspective, we provide the distribution of carbon sequestration. So as you can see, the labile DOC contributed the lion's share of the net permanent production, but it quickly decreased to almost 0, and a few of them surpassed the 1-year time limit. So except for the labile DOC, the vertical DOC contributed the second lion's share, and it also contributed the largest sequestration over a 1-year period. So I'm sorry, I forgot to see the yellow and the green line separated the sequestration time less than a year and longer than a year. So we are interested in how the climate change is going to impact the BCP. Usually we use the Martin curve to represent the POC flux. As you can see here, the function is shown by this equation. And usually if we have a higher B and most of the POC luminize in the surface layer and few them exported to the deep layer. So if we have a lower B and most of them gonna a large portion of the B POC gonna export to the bottom ocean. So previously we have empirical equation to describe the B function with the surface of the ocean temperature. We have a linear equation here. So in this study, we re-optimize the relationship using the inverse model. And what we have is the B distribution shown in this panel. We have a higher B in the tropical ocean and lower B in the Arctic Ocean. So if we extract the future temperature in the Earth system models and we calculate the B equation and do a anomaly calculation from the future prediction and the current B, we have B distribution in the bottom panel. As we can see, in most of the ocean, the B increases, which means the BCP gonna decrease with climate change. So here I have some take-home message, and I will now read them and leave it here and take questions. Hey, Katie.
Great, thank you so much, Wei-Lei. That was very interesting. Now I'll turn it over to anyone who has any questions. Either turn your video on or speak into the microphone, or you can post a question in the chat. Looks like Lauren has a question. Go ahead, Lauren.
Yeah, thanks so much. This is a really awesome talk. I was curious about you had a figure with like blue, red, and I think black with a line. It was about like model DOC versus observed DOC. Yeah, it was right here on slide 14. Yeah. And yes, and so I was curious. So it looks like the Pacific and Indian Ocean hang out on that line really well, but there's quite a bit of skew for the Atlantic Ocean off in terms of skew towards observed DOC. I was just curious what you think that is. Is that just because it's not capturing, I guess, the North Atlantic deep water? Is like that have something to do with what that skew off of the line is there?
Yeah, so it's a very good question. So actually, I don't know. I should separate this dots based on where they are, and but I haven't done so. I'm not sure whether they are in the North Atlantic Ocean or not. But apparently, the model underestimated these data points here. But I will check. I will check where these dots are located.
Yeah, that would be really interesting to know, but this was a great talk. Thank you so much.
Okay, thank you.
Great. Any other questions? Thank you for that, Lauren. Okay, Wei-Lei, I did have a question. Just sort of a more broader question. In terms of the largest uncertainty, could you speak about what remains sort of the largest uncertainty that you see in either your observations or your model parameterizations?
I mean, which one?
Yeah, that one, this slide number. There we go. Yeah.
You mean how do we calculate the uncertainty of this?
Yes, just looks like you have some differences, some larger differences in the modeled versus observations. And if you could just speak on that.
Right. So actually, compared to the field observation, our model uncertainty is smaller, and so the way we calculate this uncertainty is we use different transport operator, and also we adjust the lifetime of labile DOC. We use either 12-hour lifetime or 24-hour lifetime. So after we have a total of 4 models, and we calculate the uncertainty based on the results of these 4 models.
Great, thank you.
Mm-hmm.
All right, any other questions? No? Okay, well, thank you so much, Wei-Lei.
Sure, yeah.
Yeah, and if anyone has any further questions, Wei-Lei, maybe you could put your email in the chat.
Sure, I will.
Great. All right, thank you so much.